Have you ever wondered why, when you jump off a boat or a skateboard or any vehicle on wheels or water, when you jump one way, the object that you're jumping off moves in the other direction? It recoils. And the reason it recoils is one of the fundamental conservation laws of nature, and it's called the law of conservation of momentum. And the law of conservation of momentum says that when objects collide or are forced apart, when you jump off something or when you fire a gun, the total momentum of the whole system remains constant. The total momentum, this word here, total, is important, which we'll come to in a while, because the momentum of each individual object can change. Their velocities can change, etc. But when you look at the total momentum, that number stays the same. So a statement of the law of conservation of momentum looks like this. It says that if no external forces act, so for example friction, e.g. friction, no energy comes in, no energy goes out, the total momentum of a closed system, an isolated system with no external forces, in any particular or specified direction, always remains constant or the same. Now, obviously, an isolated system is difficult to achieve, but there are lots of approximations to isolated or closed systems where friction can be minimized. Ice skating is a particular example which comes up a lot in the exam questions. So we're kind of approximating sometimes about our closed system with no external forces acting, because friction is very difficult to get rid of, but we can still do the maths. So sometimes that total momentum, the initial momentum, and therefore the final momentum as well in total, is non-zero in the case of a collision. So things are moving before they interact, before they collide. And sometimes the initial momentum is zero. And an example of that is an explosion or firing a gun where nothing's moving beforehand. A rocket taking off, for example, is a good example where the initial momentum is usually zero. And the point about the conservation of momentum is that this does not change in total. And as I say, the individual momentum of each object might change, but the total momentum does not change. So just taking that example of a rocket taking off for a moment, we have our rocket and we have our fuel, and at the point before takeoff, when the fuel is still inside the rocket, the total momentum of that system is zero. And then the rocket takes off, and the fuel, as it's exhausted from the rocket, acquires a momentum in that direction. And in order to conserve the momentum, in order to obey the law of conservation of momentum, the rocket must gain momentum in that direction. They're opposite, so one of them has to be negative. And therefore, hopefully you can see that those two, when you add them up, will add up to zero, and the total momentum of the rocket and the fuel together will still equal zero, even though the two individual objects have non-zero momentum. The key is in the fact that it is in the opposite direction. Okay, but let's have a look at a collision where the initial momentum is non-zero. The total still remains the same, but it remains at whatever value it had before the collision. So here's a question to illustrate that law here. So we have two lab trucks moving towards each other. I'm going to draw a little diagram of that over here. Here's lab truck number 1, and here's lab truck number 2. So this one has a mass of 700 grams, and the other one has a mass of 400 grams. I'm going to convert those to kilograms immediately. Sorry, that's the wrong way around. That one has a mass of 0.7 kilograms, 700 grams, and this one has a mass of 0.4 kilograms and 400 grams. Truck 1 is moving to the right with a speed of 0.6 meters per second, and truck 2 is moving to the left with a speed of 0.4 meters per second. Now, here again, we've got objects moving in opposite directions. So I'm going to use the convention that vectors pointing to the right are positive and vectors pointing to the left are negative, which means this one must be minus 0.4 meters per second. This first part of the question asks us to calculate the individual momentum of each truck. So let's start with truck 1. Obviously momentum is mass times velocity. So that's going to give us a momentum of 0.7 kilograms times 0.6 meters per second squared, which is going to be 0.42 kilogram meters per second squared. And for truck number 2, we have the same procedure. Momentum is mass times velocity, but this time we have a mass of 0.4 multiplied by a velocity of minus 0.4, which gives us minus 0.16 kilogram meters per second. And those are our answers to that. Now then, the second part of the question says that they hit and then move together as one after the collision. So what we're going to invoke here is the law of conservation of momentum in order to try and work out what their combined velocity is after the collision. And in order to do so, we need to know the total momentum of the two trucks together. So we're going to work that out up here before we move on to part 2. So the total momentum is going to be P1 plus P2, which is going to be 0.42 plus minus 0.16. And that is going to give us 0.26 kilograms meters per second. So that's the total momentum. It's got a positive sign. I'm going to put a little box around it because that number stays the same. Whatever happens to their velocities when they collide, that total momentum, the 0.26 kilogram meters per second, is going to remain the same. That's the point of the law of conservation of momentum. So it then says they hit and move together as one after the collision. So let's draw another little diagram. We have both of them moving together. So we have here a combined mass of 0.7 plus 0.4 kilograms moving as one object. So that's going to be 1.1 kilograms. And we want to know at what speed do they now move, and also in which direction. So we want their final velocity, their combined velocity after the collision. So let's have a look at that. We can use the same equation. Their combined velocity is going to be the momentum divided by the mass, just rearranging P equals mv. But this time, because they are one object, we want to use the total momentum from before, which is going to be the same, divided by the total combined mass of the two trucks together. So that's going to be 0.26 kilogram meters per second divided by the 1.1 kilograms in total. And when we do that, 0.26 divided by 1.1, we end up with 0.24. Let's just move this out of the way a sec because it's getting a bit too close. We'll just pop that over there. 0.24 meters per second. Because this is and because of our convention of the directions that we established earlier, we can also tell from this number which direction they're going. So they're going to the right. If it was a negative number, we could tell that they were going to the left. So that's how to do basic questions on the conservation of momentum, working out the individual momentum of each object and then calculating the total, and the total remains the same whatever happens to the objects. And that is the law of conservation of momentum.